Welcome to Chapter 25 of the Universe. Momentum, Characteristics and Foundation of Locomotion. This chapter asks a deceptively simple question. Once a body has been set in motion, what is actually happening in the moving body? The chapter does not begin by dismissing the history of mechanics. It begins with the familiar idea of inertia and asks whether another concept can give a more physical explanation of how motion begins, continues, changes, and ends. The central proposal is simple. Pressure impulse is the initiating action. Momentum is the physical condition left in the body after that action. Gravity is the continuous attracting influence that regulates the motion. Galileo and Newton gave classical mechanics a powerful language for describing persistence of motion. Newton described inertia as an inherent power by which a body tends to remain at rest or in uniform straight-line motion. Chapter 25 respects that historical role, but it asks a different question. Does the word inertia itself tell us what is physically being carried by a moving body? The concern is explanatory rather than historical. If speed, direction, transfer, and eventual change are the things we want to understand, the chapter proposes that momentum is a more informative variable. This is a conceptual proposal of the book, not a claim that the historical development of mechanics had no value. The framework developed in the manuscript separates three roles. Pressure impulse is a short duration, directional action that initiates motion. Momentum is not a force, it is the physical consequence of an applied force, the motion carried by the body after the initiating action has ended. Gravity is the continuous attracting influence that regulates and curves motion. This separation matters because it prevents the cause of motion, the quantity carried by the moving body, and the regulator of its path from being described as though they were the same thing. A useful sequence is impulse, acquired momentum, locomotion, with gravity modifying the path. Momentum is useful in this framework because it has magnitude and direction, can be transferred between bodies, and can change when a body interacts with another body or gravitational influence. A collision, a rebound, a projectile, an orbit, and a spinning body all give us observable consequences of motion. The chapter therefore treats momentum as something we can follow through an event. The familiar quantitative relation remains. Momentum is mass multiplied by velocity. The proposal is not to throw away that relation, but to ask what physical meaning we should attach to the quantity it measures. The important change is explanatory. Follow the acquired motion itself, rather than treating persistence as an unexplained background tendency. The most unusual part of Chapter 25 is the proposed distinction between indispensable and dispensable momentum. In the book's terminology, indispensable momentum is the permanent quantity of matter itself, the mass that provides the capacity to receive and carry motion. Dispensable momentum is the acquired, directional motion produced by an external event, such as pressure impulse, ejection, collision, or gravitational action. This terminology is specific to the framework developed in the universe. It is intended to make a distinction that the single word momentum does not normally make. In the book's philosophical shorthand, indispensable momentum is what a body is. Dispensable momentum is what a body has. A body at rest has no velocity, and therefore no ordinary mass times velocity momentum. Yet the chapter uses the phrase indispensable momentum for the permanent presence of mass itself. The point is conceptual. Matter does not disappear when its acquired motion disappears. Mass remains as the carrier or substrate on which an impulse can act. Thus indispensable momentum is not motion itself. It is the book's way of describing the ever-present capacity of matter to receive and carry acquired motion. This is a terminology introduced by the manuscript, and it should not be confused with the standard textbook definition of momentum. Dispensable momentum is the active part of the distinction. It is the motion acquired by a body when an external cause acts. It has direction and magnitude. It can be transferred in collisions. It can be modified by gravity, friction, resistance, or another interaction. In a sufficiently isolated situation, the chapter argues that it can persist for very long periods because there is no internal mechanism by which the body simply spends its own momentum. A thrown ball, a projectile, an ejected fragment, or a drifting body can therefore be followed by asking, what momentum was acquired, in what direction, and what external influence changes it? The key phrase is acquired, directional, transferable motion. The manuscript openly describes this as one of its hardest conceptual decisions. Replacing inertia with momentum may sound unnecessary because inertia is deeply established in classical physics. But the author's question is practical. Can one variable explain what actually changes from one moving body to another? Momentum changes with mass and velocity. It can be calculated, transferred, opposed, and observed through effects. The proposed distinction is therefore not presented as a decorative new name. It is introduced because the author believes the motion of matter cannot be understood clearly without separating the permanent carrier from the acquired motion. The chapter is trying to make locomotion causally legible, not merely rename an equation. Mass becomes important immediately. If a similar impulse acts on bodies of different mass, the resulting changes in velocity need not be equal. The lighter body can acquire a larger change in velocity, the heavier body can acquire a smaller change. This is one reason the chapter regards momentum as more informative than a fixed background notion of inertia. The same event can therefore produce visibly different motions because the receiving masses are different. The impulse is the event, the acquired momentum and resulting velocity are what we then observe. In the chapter's language, mass is the carrier, and acquired momentum is the motion carried by that mass. The manuscript carefully separates pressure impulse from gravity. Pressure impulse is momentary and directional. Gravity is continuous and attractive. In the framework of the book, pressure impulse can initiate motion in a chosen direction. Gravity does not provide that sideways initiation, instead it acts toward the attracting mass and changes the trajectory. This distinction becomes especially important in projectile motion. A body receives an initial motion from an impulse. Gravity then acts on the motion, producing the familiar curved path. The chapter therefore insists on keeping these causes distinct. Different causes, different timing, and different effects. A projectile is one of the clearest teaching examples in the manuscript because several variables appear together. An initial impulse gives the body a horizontal or tangential component and, when appropriate, a vertical component. The chapter's interpretation is that gravity acts on the normal plane component while the tangential component continues. The curved trajectory is therefore not a mysterious curved push. It is the visible result of combining straight line acquired motion with continuous gravitational action. At the highest point of a projectile, the vertical component can momentarily become zero while horizontal motion continues. The body has not stopped. This simple observation becomes a bridge to the larger question of orbital motion. The same reasoning is extended from the projectile to the orbit. A body receives acquired momentum. Gravity acts inward and bends the path. For a near-circular orbit, the tangential motion continually carries the body past the central body while gravity continually changes the direction toward that body. The result is a curved path rather than a straight fall. The chapter therefore describes orbital motion as a large-scale continuation of projectile motion. Momentum continues, while gravity bends or moderates the path. The compact description used by the book is, gravity bends, momentum continues. A recurring idea in the chapter is that a body should not be imagined as consuming its own acquired momentum merely because it possesses gravity. Self-gravity holds a body together and contributes to its structure. but the chapter distinguishes that from external gravitational interaction, which can alter the motion of another body. This leads to an important picture of persistence. A projectile continues until resistance, collision, or another external influence changes its acquired motion. A freely moving body far from significant gravitational influence therefore provides a simple conceptual example of continued motion. Self-gravity shapes the body, external interactions change its acquired motion. Momentum is also presented as transferable. A hammer striking an object, a collision between balls, the rebound of a body, or a massive ejection can distribute motion among several bodies. This is why the chapter connects momentum with Newton's familiar action and reaction picture without treating momentum as a force. The force acts during the interaction. Momentum describes the motion carried by the bodies as a consequence. The same logic is extended to cosmic ejection. One pressure event can give different fragments different velocities and directions, while the source receives an opposite response. Momentum lets us follow the consequences of an interaction from one body to another. A bounce makes the idea unusually visible. A falling body acquires downward motion. At impact, its motion is redirected. If enough of that acquired motion remains available for the redirection, the body can rise again. The chapter uses the comparison of a rubber ball and a lead sphere to emphasize that different bodies respond differently to impact. The important point for the framework is that gravity itself is attractive. It does not supply a repulsive bounce. The upward motion requires a physical redirection associated with the interaction at impact. The bounce then becomes another example of acquired momentum being transferred and redirected. Fall, impact, redirection, upward motion, and then gravitational influence again. Chapter 25 also connects momentum with spin. A spinning top, coin, planet, or star does not begin rotating simply because gravity exists. The manuscript attributes spin to a torque-like pressure impulse or an asymmetric action that gives the body rotational motion. Once acquired, that rotational motion can persist unless friction or another opposing interaction changes it. This is consistent with the chapter's larger principle. Motion is created by an event, then carried by momentum. The important distinction is between orbital motion around another body and spin about a body's own axis. Linear momentum describes translational motion. Rotational momentum describes acquired spin in the chapter's framework. The chapter uses Earth as a familiar illustration. Earth travels around the Sun at roughly 29.78 kilometers per second and rotates on its axis, yet we do not experience that motion as a constant wind or force. The explanation offered is that we, the atmosphere, and our surroundings share the same acquired motion. We are not continually being left behind by Earth's motion, we are part of the moving system. The example is useful because it shifts attention from the word inertia to the actual question. What motion is already shared by the observer and the observed body? Shared motion can be difficult to sense directly. The motion is nevertheless real and measurable. The later demonstrations in the manuscript return to the pendulum because it gives a simple laboratory setting in which gravity and acquired motion interact. The bob receives an initial pull and release impulse, and then moves under gravity. The chapter argues that the same relationship can be used as a bridge toward orbital reasoning. At one scale we watch a bob swing, at another we study a planet or satellite. The numerical mechanics of the examples remain classical, while the interpretation of the cause is expressed in terms of impulse, momentum, and gravitational regulation. This is an important feature of the book. The aim is to connect ordinary observations with cosmic questions. The laboratory is treated as a small window into universal locomotion. Chapter 25 finally gathers the ideas into one sequence. Matter is the carrier. Pressure impulse initiates motion. Dispensable momentum is the acquired, directional motion that remains in the moving body. Gravity regulates motion by changing its path. Resistance, collision, and external gravitational interaction can alter or consume the acquired motion. Indispensable momentum, in the book's terminology, refers to the permanent mass or capacity of matter to carry motion. Dispensable momentum refers to the acquired motion itself. The chapter's purpose is therefore not simply to replace one word with another. It is to make the chain of cause, carried motion, and regulation explicit. Matter carries, impulse initiates, momentum continues, and gravity regulates. The most important thing to take from this chapter is not that every reader must immediately accept a new terminology. It is that the question is worth examining. Classical inertia remains an important part of the history and language of mechanics. Chapter 25 asks whether momentum can serve as a more physically explanatory foundation for locomotion because it is directional, measurable, transferable, and connected directly to events that change motion. The proposed division into indispensable and dispensable momentum is the book's own conceptual framework. Its purpose is to separate the permanent presence of matter from the motion acquired by matter. The larger inquiry continues in the chapters that follow, from projectile motion and pendulums to the structure of the solar system and beyond.